Okay, so in this lecture, we're going to start with an example from 4.5. So let me share my screen. Okay, hopefully you can see what I'm seeing. All right, so 4.5, we're looking at curve sketching using the derivative of a function. So the derivative of a function will give us a lot of information about the shape of a graph. So we saw that the first derivative corresponds to increasing or decreasing, depending on whether the first derivative is positive or negative. And the second derivative corresponds to being concave up or concave down, depending on whether the second derivative is positive or negative. Okay, so we're going to look at example 3 and 4.5. So the function we're given is f of x is equal to x e to the x, and we want to plot this. So first of all, we want to know what the domain of this is. In this case, um, as contrasted with the other examples, the domain is all of R. So in the other cases, we had the other examples, um, we had denominators, so we had to worry about division by zero. In this case, we don't have anything like that. Okay, so that's the domain. And then it's pretty clear by inspection that the x and y, the x and y intercepts are both 0. So if you plug 0 into this function right here, you get 0. And if you set the function equal to 0, that forces x to be 0. So x and y intercepts are 0. So now, kind of going back to the point about the domain, we don't have any denominators in this function. So there's no chance of division by 0. And that's precisely, or at least usually, where you get a vertical asymptote. So because we don't have any chance of division by 0, there are no vertical asymptotes. But what about horizontal asymptotes? So remember so to find the horizontal asymptotes, you're going to take the limit as x goes to infinity and then x goes to negative infinity. If either one of those limits is finite, it's some specific finite number, then you can say that that's the horizontal asymptote. Otherwise, if the either limit is infinity, you can say that there is no horizontal asymptote. So for computing, when we compute the limit as x goes to infinity, we can see that this is also going to be infinity. That's because as x goes to infinity, both x and e to the x become arbitrarily large. And so their product must also become arbitrarily large. And so must their product. So when we compute the limit as x goes to infinity of e to the x, x e to the x, which is our function, we get infinity. So there's no horizontal asymptote going to as you let x go to infinity. And if just in case you don't remember what the graph of e to the x looks like, let me just draw that. We're actually going to need it. So e to the x looks something like following. So, so this is a plot of e to the x. And as you can see, as x goes out to infinity, the height of the graph just keeps growing. So that the limit as the limit of e to the x as x goes to infinity is also infinity. And then, of course, if x goes to infinity, then trivially or vacuously, x goes to infinity, so their product goes off to infinity. What about when we take the other limit? So when x goes to negative infinity, what do what can we say about e to the x? Well, as x goes to negative infinity, just out this way, you can see that the heights are decreasing. They're approaching 0, and that's because the x-axis is a horizontal asymptote of e to the x. So when x goes to negative infinity, e to the x approaches 0. So that means we get the following, when we compute this limit, we get the following indeterminate forms, negative infinity times 0 is the indeterminate form we get. So that means we need to do some trick to get it into either 0 over 0 or infinity over infinity. And then at that point we can apply L'Hopital's rule. So the trick is as follows. So you take the limit as x goes to negative infinity of x e to the x. And as I said, when you take that limit, you get the following indeterminate form right here. So you need to do some trick, and the trick is to flip e to the x into the denominator. Sorry, that's negative infinity. So you get x over e to the negative x, right? Now what happens? Do we get the right indeterminate form? Well, let's plot. So first of all, if x goes to negative x, then vacuously or trivially, x goes to negative infinity. What about this piece right here? What is this approach? So let's just plot the graph. So we know what e to the x looks like. So here's e to the x. And when you throw a negative on the x, that has the effect of reflecting it about the y-axis. So your graph's now going to look something like, let me try my best to here. It's going to look like something like this. So as you can see, as x goes to negative infinity out this way, so this is a plot of e to the negative x. You can see that the height of the function is going up to infinity. So we get so this indeterminate form we get is infinity, sorry, it's negative infinity over infinity. So what we need to do then, so we're almost there. We basically almost have infinity over infinity, but the sign is different. So we need to make sure we throw in a negative. We need to multiply and basically multiply by a double negative. So let me write out what I mean. So we're going to have this limit as x goes to negative infinity, and we'll throw a negative in here, but just so we don't change the whole limit, we got to throw a negative on the e to the negative x. So this negative and this negative will cancel out, so we haven't changed the overall limit. But now when we look at what indeterminate form we get now we get negative infinity over negative infinity. Hence we can apply L'Hopital's rule. So we just had to do a little bit of manipulation to write it in the required form. So let's see. So now, right, anyways. So L'Hopital's rule says that you just differentiate the numerator and the denominator, and then you can compute the limit. And then possibly apply L'Hopital's rule again. In this case, we don't, because the derivative of the numerator is going to be 1, and then the derivative of the denominator is going to be, so this is chain rule. So our outside function is e to the x, so the derivative of that is just e to the x, and then evaluate at the inside function, which is negative x, and then times the derivative of the inside function, which is negative 1. So this negative and this negative cancel, and then what we get is the limit as x goes to infinity, negative infinity, I should say. of 1 over e to the negative x. Now, there's that fact I wrote about last time. So the fact is, we have the following fact. What's the best way to phrase this? We have that if, yeah, okay, so if x approaches some number a, and you're taking the limit of f of x, and you know that that is plus or minus infinity, that's the case if and only if the reciprocal function, when you take the reciprocal function, you go off to 0. So we know, so in our case, we know that, sure, I'm doing, yeah. We know that negative e to the x approaches infinity as x approaches negative infinity. So that means that 1 over negative, 1 over e to the negative x approaches 0 as x approaches negative infinity. So we know, so we compute this limit, and we know this limit. We know that e to the negative x goes to infinity as x goes to negative infinity. So that means when you take the reciprocal, it goes off to 0. So here it is, x going to negative infinity, the function goes off to the negative infinity. Then the reciprocal function goes to 0. Actually, all right. Actually, I just realized. So this is technically true, but it's even simpler. Actually, we have this negative here. Okay. Keep this fact in mind. It is true. And it often will be really helpful. But actually, I just realized this whole thing can be simplified a lot. So we have 1 over e to the x, negative x, so just flip it back into the numerator. And then it'll be very clear that this thing will go off to 0. So as x goes to negative infinity, so we go back to our original graph over here of e to the x. As x goes to negative infinity, the graph goes off to 0. It approaches 0. So that's another way of seeing it. This other way of seeing it using this fact here is entirely valid. And it is, as I said, often helpful, but we can just rewrite 1 over e to the negative x as just e to the x. So that's the simpler thing to do in this case. All right, so now we're going to look at intervals of increasing and decreasing. So am I labeling these right? Yes, it looks. Well, actually, there's a part about, okay, I skipped C, but I've always been skipping C, actually. C is about the symmetry of the graph. I haven't really been caring about the symmetry at all. In this case, there is no symmetry, so there should be a part C here. I just skipped it. All right. So let's look at part E now. So part E is on increasing and decreasing. And for that, as I mentioned at the beginning of the lecture, that really has to do with increasing and decreasing corresponds to the sign of the derivative. Positive derivative means increasing, negative derivative means decreasing. So in order to determine where it's increasing and decreasing, we need the derivative. So let's remember that f of x is equal to x to the times e to the x. So that implies that f prime of x is going to be, so we need the product rule, so it's going to be derivative of the first function, which is 1, times the second function, plus the first function times the derivative of the second function, but the derivative of e to the x is just e to the x. And now I'll factor out e to the x, we get 1 plus x e to the x. And then I think it's pretty clear where this is going to be positive or negative. So note, e to the x is positive for all x, in for all real numbers x. So it doesn't contribute to overall sign. So it doesn't contribute to overall sign. So what does determine the sign of the derivative is this other factor, 1 plus x. So it's pretty clear, I think, that f prime of x is positive if and only if x plus 1 is positive, which is the same thing as saying x is greater than -1. So what that means is f is increasing on the interval -1 to infinity. Also, I should note that -1 is the value which makes the derivative 0. So it's a critical point. So I'll point that out afterwards. So now when is the derivative negative? Well, I think it's pretty clear that it's negative if only if that first factor, x plus 1, is negative. This is what determines the sign of the derivative. So it's negative if and only if, so let's say or. So x plus 1 is negative, or x is less than -1. So we can say f is decreasing on the interval -infinity, -1. So now note that f prime of -1 is 0, so it implies that -1 critical point. And then based upon this knowing where it's increasing or decreasing, we can say in fact it is to the left of -1 you're decreasing, and then to the right of -1 you're increasing. So that means it's a minimum, or let's say it corresponds to a minimum. Maybe that's a better way to say it. So I mean that's not the minimum value itself. You have to plug the critical point into the function to get the minimal value or minimum value. But we can say it corresponds to a minimum. And that's because as I said, to the left of -1 you're decreasing, so you're going down towards that -1 point. And then to the right of it, as you go away from it to the right, towards the right, you are increasing. So this means that you correspond to a minimum. All right, so I guess this is also I kind of combine this f, so this is a local min slash max. So we already know that -1 corresponds to a minimum, so let's just plug that into the function. So it's gonna be -1, e to the -1, so it's 1 over e, local minimum. This is our local minimum. All right, so now the last thing I think we need is concavity, and then we can actually sketch this curve. So we have concavity. So now concavity, we know corresponds to the second derivative. So whether you're concave up or concave down, it corresponds to the sign of the second derivative. So we need the second derivative. So first of all, let's remember the first derivative is x plus 1 e to the x. So when we differentiate this, we had to use product rule again. So this is our first function, second function. So the derivative of the first function is just 1, so it's e to the x. And then times plus the first function times the derivative of the second function. So that's going to be e to the x. And then we can factor out e to the x. So we have 1 plus x plus 1 e to the x. And that's just going to be, I guess you could write it as 2x plus 2 e to the x. And then again, this e to the x term, or this e to the x factor, doesn't determine the sign of the derivative, so it's completely determined by this first factor right here. And then I think it's pretty clear that the second derivative is positive if and only if x plus 2 is positive, or which is to say that x is greater than -2. And having positive derivative means you're, I always get this backwards, so let me make sure I'm doing this right. It means you're concave upward, if I'm not mistaken, concave up. So we're concave up on -2 to infinity. And then for when the derivative is second derivative is negative, that's the case if and only if x plus 2 is negative, which is to say that x is less than -2. So that means that we're concave down on negative infinity to -2. So what this means is we have an inflection point at so first of all, the second derivative is 0 when x is equal to -2. So we have an inflection point at x equals -2. This is where it changes concavity at this point. Remember, concave up means that the tangent lines lie above the curve, and concave down means the tangent lines lie below the curve. All right, so let's try putting all this together. See if we can get a somewhat reasonably accurate, decent graph. So here's our XY axis, and we're going to plot f of x is equal to x e to the x. All right, so first of all, we know that the x-axis is a horizontal asymptote. Let's see. So yes, right here. So this calculation right here. So we're taking the limit as x goes to negative infinity, and we found that that was equal to 0. Did I fit that in here? So let me just rewrite it down here. So hence, just more simply, the limit as x goes to negative infinity of f of x is 0. So y equals 0 is a horizontal asymptote as x goes out to negative infinity. All right, so now we have a minimum at, let's see, is that right? Is it a minimum? Yes. We have a minimum at negative, oops. We have a minimum at -1, and we have an inflection point at -2. So -1, -2, and then we have, as I said, a minimum at -1. So what we have there, oops, is, oh, did I calculate this wrong? The minimum? Oh, there should be this negative in front. I'm just gonna keep it as negative e to the -1, actually, just be cleaner to write that. So we have a minimum point at -1 e sorry, -1 negative e to the -1. All right, so now we know that as you go out to infinity, you have to approach the x-axis, and then you have to, so we're concave up, and then at this point, so this is concave up, it's hard to tell that's concave up, but now we're concave down, so this is where it's starting to change to, actually it's not quite accurate. Let's make it a little bit clearer that it's concave up and concave down. So you, as I said, you go out to infinity. Sorry, when x goes to negative infinity, you get close to the line. You're concave up, and then you're concave down. still concave down. So you have like this change in inflection here. So you're concave up, concave down, you're decreasing all the way up till you get to the absolute minimum, and then you go up, oops, put it like that. And you go through the x-axis, or sorry, the origin, that's the y-intercept, right? And then at this point, you're just increasing within bound. So that's what the plot, that's what this graph looks like roughly. It's kind of hard to draw with this Wacom tablet. So I'll also show you the end product here. So, computer generated image. So that's what that looks like. This is of course in the book. This is figure 8, so you can also see that for yourself. All right, so I think there's one more problem, and let's see. I don't think we're gonna do any more today because that's a lot. So maybe another one of these curve sketching problems next time. Yeah, maybe one more or two. All right, so for now though, since that's very laborious problem, we're gonna move on and we're gonna do some optimization problems. So we're gonna jump to section 4.7. So this is 4.7. This is on optimization, and as I said, this is sort of like related rates, not quite. So in related rates, we had to use a lot of implicit differentiation techniques. For optimization, so related rates is that we have these two quantities that are changing with respect to say time, and we want to relate their rates. So that's hence the term related rates. In optimization, we don't necessarily want to relate two quantities. I mean, often we will. That's not necessarily the focus. Focus is we have a quantity, we have a finite amount of a quantity, and we want to either maximize or minimize that this quantity. So the last time we met, we looked at example 1 and was about fencing. So here I'll show you this. This is just to quickly review what we did. So here's the problem. We have a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest? So you can imagine there's a lot of configurations. So here's one. There's one in the middle, and there's this other one. So you can see like clearly the outer ones. So the first and the last one, they're not going to maximize the area. And you can see you can explicitly calculate these. So here you get 220,000 square feet, 400,000 square feet, fairly big numbers, but not as big as this other number. So there's going to be certain configurations that are least optimal. And it turns out that you can use calculus to figure out the optimal layout. And of course, optimal depends upon what you want. In this case, we want to optimize the area. We want to maximize it. And so that's what we did last time. So let's look at another example. So, all right. So, all right. So here's this is example 2. This is a pretty good example. As good as any, I suppose. So rather than write this whole blasted thing out, I'm gonna just copy and paste this. So what we have is here's our whoops, why isn't that? Can I move that? All right. This is where it's gonna go, I guess. So this is example 2. I guess I could move it, but I don't feel like it. So we have a cylindrical can is made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So again, there's going to be a lot of different configurations for the metal. And I want it to hold 1 liter. That's the fixed quantity. This is what we call the constraint. This is one of these constraints here. I have this constraint that it needs to hold 1 liter of oil. And you can imagine that there's probably a lot of different ways to construct a cylindrical can that will hold 1 liter of oil. So it could be really short but wide, very tall but narrow, and some of these might cost more than others, or some. And so in this case, cost more means requires more material. So we don't really care about the specific cost of these materials. More so, we care about how much of the material that we're using, because these are, cost and material used are in a sense proportional in some way. So we just need to know what's the configuration, what's the best way of assembling the cylinder that uses the least amount of metal and still allows it to hold 1 liter. Of course, this is our constraint. It's very important that we have this constraint. So there's this figure that they draw. I'm not going to even attempt to redraw it. So I'm going to just copy and paste it. This one I'll try to move around a little bit though. So let's see. I think I just go like this, maybe. Yeah. All right, so we have this figure right here. Honestly, I prefer virtual teaching. It's a lot easier. So we have this nice figure here, and as I said, we want to minimize the amount of materials you need. So first of all, we have this constraint. The volume must equal 1 liter, which we're gonna, I guess, want to convert to 1,000 cubic centimeters for whatever reason. But what's the volume of a cylinder? So the volume is V is equal to pi r squared h. And so we're saying that this is 1,000. So that's actually puts a constraint on R and H. The radius of the cylinder, like the top piece, the disc on the top, yeah, and the bottom, of course. And it puts a constraint on the height. So we have this radius here, our height there, and it's constrained, and this radius here that's constrained to satisfy this equation. So this is our constraint. It's going to actually turn out that we're going to want to completely eliminate H. So we can say H is equal to 1,000 over pi r squared. So this is our constraint. And now we want to describe how much material you're using. So how much material is used is described by the surface area, right? Described by surface area of the cylinder. And that's not hard to figure out. Let me see if I'm spelling this right. I did not sleep at all last night, so I'm experiencing a lot of brain fog right now. So how much material is used described by the surface area of the cylinder? So we'll call A the surface area. So the surface area is given by this disk plus this disk. I guess plus I don't know how this is like the cylinder part itself, I guess. So the disk has a radius of pi r squared, but we have two of them. So we have 2 pi r squared. And then we have this area of, oh, I'm being an idiot. It's just, this is literally a rectangle when you unfold it. So it's the base, so base times the height. That's how you compute a rectangle. So it's going to be 2 pi r h. And this is the reason why I wanted to solve for h, because we have the surface area depends upon h and r, but that's annoying. So we want to eliminate that. So we get 2 pi r squared plus 2 pi r h, which is 1,000 over pi r squared. Simplify this. So the two the pi's cancel, and then a factor of r cancels, so 2,000 over r. So this is what we want. Um, this is the function we want to minimize. Want to minimize this. So this will give you the radius. So the surface area depends on the radius, and once you've worked out the radius, you can figure out how much material you'll need. So we know how to. This is definitely a continuous function, so we have all the tools of calculus available. So we can use those at our disposal. So find to minimize a continuous, or to find the minimal value or the maximal value or the local minimum or the local maximum of a continuous function, you need the derivative. So let's compute the derivative. So let me just write this as a function of r. So we get 4 pi r minus 2,000 over r squared. All right, so local min occurs, let's say can occur, not guaranteed to occur, but can occur at critical points. Remember that was maybe it was, I don't remember, Fermat's theorem or something that said that if you have a local minimum or maximum, it must occur at a critical point. So we just kind of set this function equal to 0 and solve for r. So we get 4 pi r minus 2,000 over r. That's not supposed to be r squared. That's just supposed to be r. Oh no, I took the derivative. I'm sorry. So I get that, and then if you solve, let's see. I'll just get to the point, and if you solve for this, if you do the algebra, I'm not going to write it all out. You can do it on your own, and of course, if you run into trouble, go to the tutoring room or come to my office. But if you do the if you do the algebra out and solve for r, you get let's see, cube root of 500 over. That's not. Let me write the cube root again. It's not quite good. So you do, let's see, cube root of 500 over pi. All right. So first of all, let's see, do we need this back here? Oops, I don't know why that came up. All right, so I guess what you can just do is you can see observe that a prime r is negative for r less than the critical point. And a prime of r is positive for r greater than the critical point. So it implies that this implies that this critical point corresponds to local minimum. But we don't want just a local minimum, we want a global minimum. There could be a lower point. But the thing is that let's see, how do we want to write this? Oh, I guess the point is this, that it actually is let me just write this on, but this actually is the global minimum. And that's because if you're gonna have, this is a nice function, it's continuous and everything. So after this critical point to the right of it, it's just the function is increasing because the derivative is positive. So it's getting larger and larger and larger. It never goes back down to some sort of minimum. So there are no other minimums. So this actually has to be the lowest point on the entire graph. And so this radius right here. So once you can work out the amount of material you need from that number. All right, let's do one more problem. So this next one isn't really an implied problem, but I'm sure you could imagine that there are applications to this. Maybe not, it's not obvious how this applies in the real world, but I'm certain that there are applications of this. So what we have is the following. We want to find the point on the parabola. Oops. Find the point on the parabola. Y squared is equal to 2x. That is closest to the point 1, 4. So we want, what we want to do is we want to minimize distance between 1, 4 and a point xy on y squared is equal to 2x. And then we want to work out what that point has to be at. What is this? What are the coordinates of this point? So so the distance between these 2 points, we'll call it d, is given by using the distance formula. So the distance formula is that you take the difference in the y coordinates. Sorry, yeah, it doesn't really matter. Difference in the x coordinates. So x is equal, so we can get what? Sorry, let me back up. So the difference in the x coordinates. So x minus 1 squared. So the difference in the x coordinates squared plus the difference in the y coordinates squared, and then you take the square root. But we can eliminate x because remember the xy is a point. Xy is a point on here, so the xy have to satisfy this equation, so we can eliminate x actually. So x is going to be y squared over 2 minus 1 squared plus y minus 4 squared. Now, this is going to get awful because you want to minimize this function right here. But it turns out that if you can minimize the square, you can minimize d squared, then you can minimize d. There's like this correspondence between d and d squared, so we can just get rid of the square roots. So really the function we want to minimize, really we want to minimize, whoops, that's not how you spell that. Minimize this function, which is going to be f of y is going to be d squared. So what we want to do is minimize this function d squared, and d squared is going to be y minus 2 1 squared plus y minus 4 squared. And so now we just, again, we have this continuous function, we want to minimize it. So we can just use calculus. We can use all the tools we can use tools of calculus to find these values. So we take the derivative to find the critical points, and this is where you could have a minimum or maximum. So we use for this we use chain rule. So we have this 2, so we bring the 2 down, y minus 2, y over 2 minus 1, and then reduce the power by 1 to get 1, and then take the derivative of the inside function, which will be 1/2. And then chain rule again, times 1. And then we can simplify. So this 2 cancels with this 1/2, so I just get y minus 2 minus 1 plus 2y minus 8. And then what do we get? So we get 4 over 2, so it's 5. Sorry, yeah, so write this as 4 over 2. So then when you add it with the y over 2, you get 5y over 2 minus 9, but that doesn't seem right. Maybe it is. Anyways, so that implies that the critical value is given by, so it would be 18 over 5. That doesn't seem right. Looking at the book. Oh, wait. I see what I did wrong. All right, I wrote down the wrong function. So d squared is not quite this. It's not y over 2, it's y squared over 2. Okay, that makes sense. All right, so let me erase all this. Oh, that's annoying. All right, so let's do that again. So this is our y, and so f prime of y. So sorry, this is f of y. So f prime of y is going to be 2y squared over 2 minus 1 times I guess y plus 2y minus 4 times 1. So now this 2 cancels with this 2, and then we have a y squared times a y to get y cubed minus 2 plus 2y minus 8. And this looks a lot better. So we get y. Wait, why do I have this? Oh my goodness, okay. Sorry, I messed up a little bit, not that bad though. So we get the y cubed, yeah, so, and then it's going to be minus 2y, not just 2, it's going to be 2y, plus 2y minus 8. These cancel, and then you just have 8 left, negative 8. So that implies that y is equal to 2 is a critical point. So this is where minimum or maximum could occur. Not guaranteed to occur there, but just could. So we have to use the first derivative test to determine whether or not this is a minimum or a maximum. But it's pretty clear that when y is greater than 2, f prime of y is positive, so it's increasing on 2 to infinity, and then when y is less than 2, f prime of y is negative, so this means it's decreasing on 2 to infinity. So what we know then is that this f prime of 2, which is going to be, well, sorry, this implies that we have a local minimum at y is equal to 2, right? Because we're To the left, wait, I didn't write that right. This should be negative infinity to 2. So to the left of 2, we're decreasing, and then to the right of 2, we're increasing. So y is equal to 2 corresponds to local minimum. So we have a local minimum at this point. And then we can say, so now that we know the y coordinate, we can find the x coordinate. So if y is equal to 2, then we have that equation y squared is equal to 2x. So that becomes 4 is equal to 2x. And then that implies that x is equal to 2. So 2 comma 2 is the point on the curve y squared is equal to 2x closest to 1, 4, and with distance, we can actually say what the distance is. D is equal to the square root of f of 2, and when you plug 2 into this function right here, you get 5, according to the book. So it will be a distance of root 5. All right, I think that's enough. Let's see. So next time it looks like we'll do one more curve sketching problem, and then maybe one more optimization problem, and then we'll get to what's called are called antiderivatives, and this is really like the start of talking about integrals, which is the next main topic of calculus, and it's going to seem like a completely different concept in the idea of an integral, but it's actually going to turn out that integrals and derivatives are in a sense dual to each other, or inverses of each other. You can actually you can make that a little more precise and actually just say they are inverses of each other. And I'll say a little bit about that. Why in derivative and the integral are just the inverses of each other. So that's all for now. So let's see, stop sharing.